Hello, everyone. I am recording some short videos for you to help with 5.4 and 5.5. I know we had to go pretty fast through this in class, so I wanted to give you some resources. So this one in 5, we're going to focus on these two tough ones here, integrating both an absolute value and a piecewise function. Um, so we did do this in class, but it was kind of quick, and I wanted to give you an opportunity to see it again with an explanation in case it was just too fast the first time and it didn't quite make sense. So I'm going to come back to the absolute value here in number 4 because that's the toughest one. I think that uh, the piecewise function is going to make a little bit more sense for you. And this is from the in-class worksheet that I handed out today in class. So I just wanted to kind of go through these with you. All right, so number 5, we are integrating from 0 to 2 pi f of x dx. And the function that we're integrating, f of x, is a piecewise function. It looks like sine of x, but only for values of x that are less than or equal to pi. And it also looks like -2 times the sine of x for values of x that are greater than pi. So in order to figure this out and how to integrate this and find the area underneath this, it's important to remember how piecewise functions work. So to graph piecewise functions, this function is going to look like y equals the sine of x, but only for x values that are less than or equal to pi. So pi is going to be an x value over here somewhere, and anywhere from here over to the left, my function is going to look like y equals the sine of x. And then anywhere to the right of pi, for any x values that are greater than pi, this function is going to look like y equals -2 times the sine of x. So if I'm finding the integral from 0 to 2 pi of this function, I'm finding the area between f of x and the x-axis from 0, which is over here, to 2 pi, which is over here. Now, if I'm finding the area between these, then we have to kind of be careful because from 0 to pi, the function looks like y equals sine of x. So the area that I'm finding is going to be the area between sine of x and the x-axis. But if we are bigger than pi, from pi to 2 pi in my interval, I'm finding the area underneath this other function from -2 sine of x down to the x-axis. So because my function switches there in the middle, we're going to have to cut this up into 2 pieces. So we can go ahead and do this. We're going to write this as 2 integrals. So in order to evaluate this whole function from 0 to 2 pi, I have to do this in 2 pieces. So the first part of this is going to be the area underneath the sine of x. And the area that's underneath this function in my interval is just this part from 0 to pi. So that's the area that we're going to find from 0 to pi. And then we are going to add to that the integral from pi to 2 pi. And from pi to 2 pi, the area that we're finding is going to be between -2 times the sine of x and the x-axis. So that's the function that we are going to integrate from x equals pi to 2 pi. And it kind of came up in one of our classes today that the question was whether or not we needed to make sure that this whole thing was continuous at pi before we split these up. And the answer is actually we don't need this to be continuous at pi in order to split these up. Really, we just need this function to be integrable in order to split it up because we are using our linearity rules. Well, yeah, they were linearity rules that said if we're integrating something from a to c, as long as our function f was integrable from a to c, we could split this up and go an integral from a to b of that function plus an integral from b to c of that function. And we just needed our function f of x to be integrable over a to c to be able to do that. And we are integrable if our function's continuous everywhere or if we have finitely many jump discontinuities. So even if we weren't continuous and we had a jump discontinuity at pi, this whole f of x function would still be integrable, and we would still be able to separate this into two pieces. The continuity bit comes from, I guess I don't have it in this one, comes from the fundamental theorem of calculus part 1 that says in order to evaluate each of these integrals with the fundamental theorem of calculus part 1 that says we find the antiderivative and then plug our bounds in, each of these functions needs to be continuous on its interval here. And the sine of x is definitely continuous everywhere, so it's continuous on this integral from 0 to pi. And -2 times the sine of x is also continuous everywhere, so it's definitely continuous on its interval from from pi to 2 pi. So this meets all of the requirements to both split it up and to be able to apply the fundamental theorem of calculus part 1 to each of these separate integrals to evaluate them. That question came up in class today, and I don't think I was able to find the right words to explain that clearly enough. So I wanted to make sure that was clear. Okay, so now to find this area, we've split this up, and now we're going to evaluate each of these integrals with the fundamental theorem of calculus part 1. So the noodle says find the antiderivative. So I'm going to say, all right, what function has a derivative of the sine of x? If the sine of x is my derivative, what did my OG have to be? And I know that it's got to be negative cosine of x. That's going to be the function that has a derivative of positive sine of x. That's my antiderivative. I can pick any one that I want. So I'm going to pick the one with c equal to 0. And then I'm going to add my vertical evaluation notation from 0 to pi. And while I'm in antiderivative mode, I'm going to go ahead and do my second one as well. So the noodle says find the antiderivative. And I'm going to ask myself, what function has a derivative of -2 times the sine of x? What function could I take the derivative of to get -2 times the sine of x? Well, I know I'm going to have a 2 in it. And I know that the derivative of cosine is negative sine. So I'm going to need 2 times the cosine of x, and that should do it for me. Again, I'm going to pick a c value of 0 because I can pick any one I want with a definite integral. And now I'm going to evaluate this from pi to 2 pi. And now we are done with the antiderivative part, and now we'll do the evaluation part. We're going to plug in the top, and then we'll plug in the bottom and subtract them. So for this first one, I'm going to plug in pi, so I'm going to get negative cosine of pi minus negative cosine of 0. That's the evaluation of this first bit, plus I'll do the evaluation of the second bit, and I'm going to get 2 cosine of 2 pi minus 2 times the cosine of pi. And now we just have to use the unit circle for this. Okay, so pi, just do a quick unit circle over here. Pi is over here, which is going to be -1, 0. Cosine is the x coordinate, so negative cosine of pi is going to be -1 minus negative cosine of 0. 0's over here, which has an ordered pair of 1, 0. The cosine of 0 is 1, so negative cosine of 0 is negative 1. And then I'm going to add to that 2 times the cosine of 2 pi. 2 pi and 0 are in the same spot, so the cosine of 2 pi is also 1. So 2 times 1 is 2. And then it's getting a little tight here. Minus 2 times the cosine of pi. Again, the cosine of pi is negative 1, so I'm going to have minus a negative 2. And now I have to fight through all the negatives here. So a negative negative 1 is going to be a positive 1. Minus a negative 1 is plus another 1. Plus 2. Minus a negative 2 gives me plus another 2. And that gives me a grand total of 6. So I have a total of 6 square units of area underneath this beautiful piecewise function. So again, to evaluate a piecewise function, split it up over your interval if you need to. If your interval includes this breaking point here, and include each of the pieces for each function, and then you'll evaluate each integral separately. All right, now let's jump up here and we are going to do, I'm going to make a little bit of space here. We're going to do the absolute value here. Now, the hard bit about absolute values is that an absolute value itself makes all of the area positive, but we can't evaluate an integral with an absolute value in it. So we have to figure out how to manually make area positive by writing integrals without an absolute value in them. So in order to figure this out, I have to figure out where this function has positive area, where my function is above the x-axis, and where this function has negative area, where this function is below the x-axis. So to do this, we are going to start by figuring out where this function hits or crosses the x-axis. That's going to be finding our x-intercepts, right? The places where we kind of touch or cross the x-axis, those are x-intercepts. And the function that we're looking at here is y equals x squared minus 1. Again, I want to be able to write this without absolute value bars, so I'm just going to consider this function inside. And we have to find the x-intercepts of this. So to find x-intercepts, you set y equal to 0. And you're going to solve this out. You can either factor x squared minus 1 as a difference of squares, or you can add the 1 over and take the square root of both sides. Either way, you're going to get x equals plus and minus 1 for the solutions there. That means my x-intercepts here are 1 and negative 1. So here's my x-intercept of 1. Here's my x-intercept of negative 1. And now we have to figure out where this function is above or below the x-axis. To do that, we're going to pick some x values between and around each of these x-intercepts, and we're going to plug them into my function here to figure out if my y values are positive or negative. That's going to tell me if this function is above or below the x-axis there. So my favorite number to the left of negative 1 is x equals negative 2. My favorite x value between negative 1 and 1 is x equals 0. And my favorite x value bigger than 1 is going to be pi. And now I'm going to plug each of these x values into my function over here. And if x is negative 2, that means that y is going to be negative 2 squared minus 1, which is going to be 4 minus 1, which is 3. That means I have a y value of 3 up here, and I know my area is going to be above the x-axis there. All right, and then now I'm going to plug in x equals 0 to my function to figure out what y is. So I'm going to do y equals 0 squared minus 1, and I'm going to get y equals negative 1. So since I have a negative y value, that means my function's below the x-axis in between here. And now I'm going to plug in pi, and I'm going to get y equals pi squared minus 1. Well, pi is 3, a little bit, it's 3-ish, right? So pi squared is 9-ish, and 9-ish minus 1 is going to be 8-ish, right? And so if y is 8-ish, that means y is positive. It's up here somewhere. Again, I know that's not perfect. You could put it in a calculator if you wanted to, but it's going to be close to 8. And it's going to be positive. So I know that my function is above the x-axis here. And in class, I got the question of, will these always alternate like this? And the answer is not necessarily. So make sure you test every piece because they don't always alternate, unfortunately. Okay, so now we are going to break this up into pieces, just like we did with that piecewise function down below. So we are finding the area from 0 to 3. So I'm starting here at 0 and I'm ending over here at 3. Now notice from 0 to 1, I have negative area. And then from 1 to 3, my area is positive and above the x-axis. And so we're going to have to split this up into 2 integrals. One integral is going to cover from 0 to 1, because that's where I have negative area. And then the other integral is going to cover from 1 to 3, because that's where I have positive area. And the function that I'm going to integrate is this guy without the absolute values. Again, we are going to do this without putting an absolute value back in here because I can't integrate an absolute value. So we're going to find the area under x squared minus 1 in each of these. And then we just have to manually make sure all of this area is going to be positive. Now, this one from 1 to 3 is already positive, which is good. I don't have to touch that one. But this integral from 0 to 1, this has negative area, and I don't want it to have negative area. I want it to be positive area. So to make this positive, it's currently a negative. I need it to turn positive, so I'm going to multiply by a -1. You can multiply by that -1 inside or outside the integral. It's totally up to you. It's a choose your own adventure. But once we multiply by that -1, that's going to turn this now into positive area, and all of my area is now going to count as positive, just like I wanted it to. And now that this is split up into 2 pieces, we can evaluate each of these separately. I'll rock through that real quick. And so just because for space reasons, I'm going to go ahead and distribute this -1 here really quick. And I'm going to get negative x squared plus 1. That's the function that I'll integrate here. So if I find the antiderivative of that, I'm going to add 1 to my exponent and get x to the 3rd, and then divide out front. Plus the integral of 1 is just x. And I'm going to evaluate that from 0 to 1. And I'll do the same thing over here. I'm going to find the antiderivative of this, and it's going to be very similar. I'm going to add 1, divide by that new exponent, minus the antiderivative of 1 is x, and I'm going to evaluate this from 1 to 3. And now I can plug my bounds in. So I'm going to plug my 1 into this first one, and I'm going to get -1/3 times 1 to the 3rd, which is just 1, plus x, which is 1, minus. Now I'm going to plug 0 in there. -1/3 times 0 to the 3rd plus 0. And now I will add my bounds plugged into the second one, and I'm going to get 1/3 times 3 cubed minus 3 minus 1/3 times 1 to the 3rd, which is just 1, minus 1. And now we have to evaluate all of this. So I'm going to be really careful here. Negative 1/3 times 1 is negative 1/3 plus 1. And then minus, this is 0. That goes away. This is 0. That goes away. That whole thing is 0, so it's gone. And then I'm going to have plus 1/3 times 3 to the third. 3 to the third is 27. 27 divided by 3 is 9. Minus 3. And then I'm also going to do this and remember to distribute this negative. I'm going to subtract 1/3 times 1 to the third, which is just a negative 1/3. And I'm going to subtract a negative 1, which turns that into a plus 1. Okay, and nothing here is just going to straight up cancel, so I'm just going to have to add all of these. You could put these in a calculator if you want. I'm going to go ahead and get common denominators, so I'm going to get negative 1/3 plus 3/3 plus 27/3 minus 9/3 minus 1/3 plus 3/3. And so negative 1 plus 3 is 2. Plus 27 is 29. Minus 9 is 20. Minus 1 is 19. Plus 3 is 22. I get 22/3 out of this. So it's going to be a little bit bigger than 7. And I just did that in my head, so if I made an arithmetic error, I'm really sorry about that. But it looks good to me right at the moment. So I'm hoping that is all legit, but it's been a long day, I'm not gonna lie. So that is our process for evaluating absolute values. Again, you're gonna split this up into pieces, figure out where you have positive area, figure out where you have negative area based on if your function's above or below the x-axis, and then evaluate, before you evaluate, make sure any intervals that have negative area, when you set up your interval or your integral, multiply that section by a -1 to bring that negative area back positive. All right, I hope that helps you in 5.4 with evaluating the absolute values and the piecewise functions. I'll see you next time.